Hello guys, today we'll discuss about harmonic reductions. In the previous topic, that phase displacement control of a single phase bridge inverter, we derived a formula for instantaneous output voltage that is given by VAB equals to sigma n 135 to infinity 4 Vs divided by n pi sine n beta by 2 cos n of omega t minus beta by 2. That is equation number 1. And this equation indicates the nth harmonic. And that can be eliminated by choosing a displacement angle, that is beta, properly. Now, sine n beta by 2 equals to 0 if then beta equals to 360 degrees divided by n. Now, and the third harmonic will be eliminated when n equals to 3. Then beta equals to 360 degrees divided by 3, that is 120 degrees. So when the displacement angle beta equals to 120 degrees, the third harmonic can be eliminated. Now, a pair of unwanted harmonic at the output of single phase inverter can be eliminated by introducing a pair of symmetrically placed bipolar voltage notches. The first method, by placing bipolar voltage notches. So you can observe in the waveform that from 0 to alpha 1, alpha 1 to alpha 2, there are two notches introduced in the output voltage waveform. Then the Fourier series of output voltage can be expressed V naught equals to sigma n 1 3 5 to infinity Bn sine n omega t. Let this be question number 2, where Bn equals to 4 Vs by pi of 0 to alpha 1, we have a notch, that is sine n omega t d omega t, minus alpha 1 to alpha 2 sine n omega t d omega t, plus alpha 2 to pi by 2 sine n omega t d omega t. That is equation number 3. This is for quarter of the wave. Now, when you solve this by integration, you are going to get that equals to 4 Vs by pi of sine is minus cos. So, minus cos n alpha 1 by n plus 1 by n minus cos n alpha 2 by n plus cos n alpha 1 by n plus minus cos n 90 degrees by n plus cos alpha 2 by n. When you solve this, you will be getting 4 Vs by n Bn equals to of 1 minus 2 cos n alpha 1 plus 2 cos n alpha 2 divided by n. That is equation number 4. Now, we can extend for n number of notches for quarter wave. Then Bn equals to 4 Vs by n pi of 1 minus 2 cos n alpha 1 plus 2 cos n alpha 2 minus 2 cos n alpha 3 plus 2 cos n alpha 4 minus and so on. That is equation number 5. Now, to eliminate third and fifth harmonics, if B3 equals to B5 equals to 0, then we can eliminate third and fifth harmonic. So, from the graph, we can see that we have introduced two pair of notches. We equate equation 4 to 0 for B3 equals to B5 equals to 0. Then we are going to get 0 equals to 4 Vs by n pi of 1 minus 2 cos 3 alpha 1 plus 2 cos 3 alpha 2 for third harmonic. Then for fifth harmonic, 0 equals to 4 Vs by n pi of 1 minus 2 cos phi alpha 1 plus 2 cos phi alpha 2. From this we are going to get alpha 2 equals to 1 by 3 cos inverse of cos 3 alpha 1 minus 0.5, and from this you are going to get alpha 1 equals to 1 by 3 cos inverse of cos 5 alpha 2 plus 0.5 will be sixth equation. These equations can be solved iteratively by initially assuming that alpha 1 equals to 0 and repeating the calculation for alpha 1 and alpha 2. Then the resultant will be alpha 1 equals to 23.62 degrees and alpha 2 equals to 33.3 degrees. So by introducing notch 1 at alpha 1 equals to 23.62 degrees and notch 2 at alpha 2 equals to 33.3 degrees, we are going to eliminate the third and fifth harmonics in the above shown waveform. The unipolar voltage notches are introduced in the output voltage as shown in the waveform here. Then the coefficient Bn is given by 4Vs by n pi of 0 to alpha 1 sin n omega t d omega t plus alpha 1 to alpha 2, that is pi by 2 sin n omega t d omega t. Let this be equation number 7. When you solve this, you are going to get Bn equals to 4Vs by n pi 1 minus cos n alpha 1 plus cos n alpha 2 divided by n. 4Vs by pi of this. Let this be equation number 8. Then, if you follow the same pattern as we followed previously, that to eliminate third and fifth harmonics, the Bn, that is B3 and B5 should be equals to 0. Then we are going to get the equations that 1 minus cos 3 alpha 1 plus cos 3 alpha 2 equals to 0 and 1 minus cos 5 alpha 1 plus cos 5 alpha 2 equals to 0. Now, by solving this by iterations, we'll get alpha 1 equals to 17.83 degrees and alpha 2 equals to 37.97 degrees. So, by introducing unipolar notches, one notch at alpha 1 equal to 17.83 and another notch at alpha 2 equals to 37.97 degrees, we can eliminate the third and fifth harmonics in the output voltage. The modified sinusoidal pulse width modulation technique can be applied to generate the notches, which would eliminate certain harmonics effectively in the output voltage. Here we have the output voltage for modified sinusoidal pulse width modulation, and the notches of 3. Here it is introduced unipolar ones, that is, one is at alpha 1, another is alpha 3 and another is at alpha 5. So the duration is from alpha 1 to alpha 2, alpha 3 to alpha 4, alpha 5 to alpha 6 in the figure. This is regarding the harmonic reduction. If this video is useful, please like, share, subscribe.